a library that Gunnar developed with called Mixie, which is what we'll use for our Thorpe skill activity. But there's a library if you want to use it on Python for calculating, doing fine scale parameterizations. This is a good example of code you can use or some functions you can use. So feel free to download that and play around with it. Obviously, we didn't have time to actually look at it today, but this is definitely something you can work on with your groups. I don't personally do this kind of stuff, so I've largely just used Charlotte's code and got some help from her to set it up. But I'm happy to answer questions. I spent a little bit of time reading the theory, but obviously not an expert. And I'm sure maybe there's other people in the room who have also thought about this and would be doing so. Any questions about the workbook, fine scale parameterization stuff? And what we'll be working on today is also in the course materials for week 3. It's everything in the stop scale library. So I apologize. I did try to see if I could get it to work on Colab, but it just kept failing for me. Could not download the Mixie library onto it. So we'll probably just do it on Visual Studio Code. If you have problems with running Python on your computer, feel free to share a laptop with someone who works on Python and you guys can work on it together. So yeah, all of the code for that lives here. Everyone can take a minute to download it. I'll start off by doing like a quick introduction to Thorpe skills. This is all stuff that Gunnar was meant to kind of talk through with you all, because he's worked a lot with these kind of, he's done these calculations a lot before. So I'll just do my best to try and convey what he had done. Yeah, so once everyone's had a chance to download this folder, let me know. You just give me a thumbs up. While you all are doing that, I will pull up my other. And I'm sorry, Zoom people, I completely forgot to share my screen. Screen 2. And for Zoom people, can everyone see my screen? Okay. Okay. This is where the code for that library lives. I can put this on the chat as well. Let's see. So that's good. Just make sure you have that folder downloaded before we get started. Okay, so I'll do a very quick run through of Thorpe scales. The workbook will actually go through these concepts in a lot of detail. So hopefully you all will get a little bit more of a sense as you work through the code of what Thorpe scales are, but I'll do a quick introduction. Yeah, so say we don't have all our fancy instruments that we were working with last week. What if you just had temperature and salinity, just a standard instrument that measures the CTD instrument, basically? Can we say something about mixing in the ocean for that? So one thing we talked about a lot, and one of the ways in which you could make the ocean unstable is to tell the unhooked instabilities. And so those actually drive overturning stratified fluids. They create these unstable density gradients. So this is an example of one from a simulation. As you can see, that I think these colors are actually temperature, but assuming a case where temperature is largely driving density, you can see that over time, in this case space, but over time as well, you start seeing these kind of overturning because in the kind of interface between the two units. And as these stabilities develop, so you go to the next step with time, you start forming secondary instabilities, you start becoming gravitationally unstable, and those things eventually mix. And that's the final kind of stage of the fluid is sort of this really next stage of graphically stable and some homogenizing. And this is epsilon and pi. So the second panel is epsilon, the third panel is pi. You can see it's really strong epsilon pi right around there. You can see that heat and mixing, and then as things start quieting down, that dissipation values die out. So what Thorpe had an idea was think about how much mixing is driving the displacement of water bodies. So say you have this sort of stable situation, right? And hopefully everyone kind of sees that this is unstable, right? You have something that's denser over lighter, not very gravitationally stable. So Thorpe's idea is we have something called the Thorpe displacement. Basically, gives you a measure of how much, say, a particle that's something that's stable, denser, G, has to travel to reach a state where it is sort of when that is in equilibrium, so it's sort of in a stable state. And similarly, this water parcel that's sort of lighter than the surrounding fluid, how far up it has to travel to kind of reach a state where it's in equilibrium. And so, as you can probably see, so the displacement that this example water parcel has to do is negative in the case of the top dense layer, stable dense layer, positive on the sort of in the kind of lighter than layer stable. And this is the equation for that. It's just I guess would be square of that. Any questions about that? That is really the main idea of this measurement. This is the sort of measuring part of it, is how to get those displacements. And then generally, when we think about this is an energy cascade, right? You ought to probably see this a couple of times now, where in measuring really sort of, and Anwar talked about this a little bit, right? We're covering some of the inertial substrate into this kind of viscous drop off. That's really where we have been looking at our measurements at the Commonwealth scale. And again, if you don't have these sort of fancy kind of structural measurements, you can still think about what would be the potential largest values that you can plot. So that is controlled by the amount of stratification in the fluid. And that is all the on the scale. So that's the equation for that there. It depends on epsilon, dissipation of turbulent kinetic energy, and stagnation. And what Thorpe did was to relate that scale displacement to say that that was proportional to the Archimedes scale. And I will write this up because I think it's easier to do on a board than it is. Here we go. So his idea was that the Thorpe scale length is proportional by some constant of alpha to the Osmondorf scale. And if you remember, the Osmondorf scale is just on half and you do some shuffling around and try to get this in terms of epsilon, that's epsilon half. Let's see how well I could do math on a board. And you square this, so you get epsilon. Simple algebra, and that we just call it some constant C naught here. Does that make sense? It's kind of, the idea is pretty intuitive, I think, just to sort of make the case that these large scale displacements in fluid that are just observations of unstable density can then be related to the scales at which you'd expect turbulent eddies to form. Feel hopefully intuitive. And then lots of people have done, this is an example of them, and how these Thorpe scales compare to Osmondorf scales, which you can get if you know dissipation, which in our case we do. And they tend to show fairly good agreement if you have assumed some constant value. So this idea seems to work generally. Obviously, there's some caveats to this method. One is that you need to have the right vertical resolution for the density profiles you're measuring. Say your stratification is really strong, very unlikely that you'll have really large density overturns, right? It's just harder for a turbulent eddy to form. So in a lot of cases, you tend to use sort of the raw measurements. So usually when we process our measurements, we tend to pin it to a certain vertical resolution, usually recommended to kind of use the raw values right at the sort of sampling rate of the instrument. We will not do that, but this is something I'm very happy to help you kind of do this if you want to do it with this project. It's all saved. It's just not, I'm happy to show you where the variables are for the exercise. You kindly will know that. Yeah. The other thing is that the Thorpe scale is a sort of statistical average of mixing, right? So if you were to imagine us profiling this, right? Say we're on a ship right at the top, or just kind of continuously toiling and profiling the sense of the overturn. With our epsilon meter, we're getting different stages of this overturn over time as well. And so the measurements of dissipation are really kind of correspond to that specific time at which we made the measurement. Whereas the Thorpe scale measurement is more giving you a sort of average sense of how much mixing happened because of that. So you really kind of need to see a lot of mixing events together to really get a sense of what the participation values are. We'll see an example of that in the workbook. Hopefully helpful to illustrate that. And the other one that Gunnar's mixing library thinks about a little bit is how to calculate stratification. And so the way the library works is if you have something like a density overturn, it will try and identify like what the overturn is. It has an algorithm to do that. And then it will, to figure out the stratification you need for this calculation. One of the ways it does that is by just calculating the stratification across these two temperature salinity endpoints. There's a bunch of other ways to do it. And there's some discussion of that in the workbook. So this is one way you can play around and see how different it is. And I just took kind of, Gunnar also has a sort of very thorough overview of all of these different methods in a workbook on the MIXI GitHub. I won't go into a lot of those details just in the interest of time, but if you're interested, you can have a look at the documentation for that function as well. But yeah, so this is moving on to kind of using our Python library, doing some coding. So the kind of goals of this activity, and again, I put the link to the documentation for the function if you're confused. Feel free to save that. I'll put it in the chat for the Zoom people. So basically what we're going to do is kind of the library will walk through one example of the profile, how to based on that. And we can compare that with measurements.exe, see how similar they are. And then since we have both of those, I can actually compute Thorpe and all of those skills, and then also computing kind of scaling, which is this value here from our methods to see how it works out. This is using data from the Bay of Bengal, which is a very stratified basin, and so the salinity is stratified because we've got a fresh water in that basin. So you'll see that there's some of these caveats that I talked about will come on as you look through it. Any questions? And I think a couple of you have worked on this before. Grant and Camilla maybe have worked on these MIXI functions before. But yeah, so if you have questions about how to get those to work. But I thought we can start with just looking at the workbook itself. Let's see if I come on. Oh, there we go. So there's a little summary of what I just said. If you need to look back at equations and things. And this just walks through an example. You just kind of have to run this code. And we'll get to the first sort of question, which is here. So let's, once everyone has had a chance to run the code, let me know once you reach this point, and I'll give you some time to think about how. And here, I will put the equation on the board as well. Oh, yeah, yeah, yeah.
I'm wondering there would be good, and it does have a check for that. I haven't seen it. But I think I haven't seen it. That's all. So I think maybe we need to do some. Geometry. I'm just uninstalling the C. Just not to remove and then C. Good. Yeah, yeah. Well, and once like, well, did you make like concepts?
Yeah, I think also, we didn't, okay, yeah.
Okay, well, that's what I was gonna, I usually try it out first, so I just say, students real good.
No, exactly, that's all I'm working on my,
Okay, okay. All right, so you did it. Let's see. Or two months. No, so I got to see it. Yeah. Yeah. That would, yeah, that was like something.
Exactly.
So that's weird. I think it's the correction for it. Side. Well, I don't think I should get.
You tell. Tommy, does it say a specific version of Python? It's weird that it's working for me, but not
It
anymore.
shouldn't matter though. I'm gonna check the script where it does the import for thing. Because so basically on GitHub, that's cool. They have a check to see what version of SciPy you're using.
Okay,
They'll give you a different import on that. So I'm checking to see if where we solve PIP has that same
Oh,
problem.
I see. Okay.
Because then if that's the case, then we could just download the GitHub
Yeah,
repository and do it now.
okay.
I'm trying. Yeah, let's.
But Tommy really is. Um,
We can have to check to see if we're using above side by one space. You then should be using the right. I think what's happening is because, so if Honda both go to some repository, they don't know this stuff, but that's not always up to date with what's happening with GitHub. So GitHub usually has the latest code, and the content person who made the code, they even reports and then for content. But we're kind of not necessarily similar. So we might just do it in a version. Sorry if that was lengthy. You're like, I didn't know. No, that is. I never really understood. Yeah, I know. Yeah. Where's the Matlab code? Yeah. I did Conda first, and I created a new environment, just saying, try Pip, and Pip also has the same problem. According, for so far from what I've seen, though, when, I know Ankitha said that you tried Pip with one network.
that tip worked for me and I haven't had issues running this library, actually, so.
I don't know. That, yes, yeah. So that's what I'm trying to look right now, because they'll get, so we might just have to go to GitHub has the shiny thing. So it just might be thrown, I mean, if you guys want, I'm just curious now, but if you guys just want to clone the GitHub repository.
That's what I just did.
Yeah, that's still didn't work. How are you putting that?
Yeah, cause I, oh,
Oh, wait, sorry.
Yeah.
So I forced it to my GitHub and then. In the environment.
No, so this is something for version two. That's what they're doing. So that's just for changing, or you actually put the environment on now. So if you go back to your, go to Python. No, just type Python. First, let's see, import Python. That I got. We're going to import this Python. This one is for version. Got the wrong one. Two. Now if you do an import this.
has anyone actually gotten it to work?
Looks like it can work.
Okay.
Yeah, so normally there's, I think it's working on, so I can ask it, but, because there's also an issue of paths, so, you know, your, one.
Yeah,
Okay,
I'm actually-
okay, actually.
No,
That's good, so. Yeah, so.
but
Okay.
then I just have to.
But here's the problem, so do control V. Yeah.
I didn't realize not scripts would be, Mixie would be a problem, so apologize.
So it should be that. Might be another way. You know that. Yeah, it should have all the chat. Oh, you might have sound. Yeah, actually, this is not.
So for people having issues, Tommy's troubleshooting.
Yeah. I did,
This might be, but we should look at the other part of the
that's what I do. But
Need to see.
Did it work?
Okay.
Oh, yeah, it's not sure it's that.
Yeah, can you stop? But those cycles. Yeah, did you work into your special? Okay.
Oh, yeah.
I was looking. Yeah.
You did that already. We did that. Yes. We were testing for
So what's the? So what's the? It's all dry, so, yeah. Oh, okay.
This is.
Oh.
Oh, you're not. Oh, sweet, yeah, we should chat that, it's all time. Yeah, it's just like. Yeah. I'll take that. Here. Now it's like.
So, why don't we some of us go ahead and?
That's weird, yeah. Cool, nice.
Yeah, I think we have.
Yes.
So when you did,
So, we're just like this little like put down this one for all. So
okay.
so we can clone.
We just get
These small things.
keeping the
Or you could just, or you don't do it, you just stop. Yeah, that's.
That's
what
what
I use. Oh.
I don't know what we're talking about, but when I don't see it, okay, so. Yeah, I just, I don't know. Yeah.
Yeah, yeah. Do it again, yeah. No, I mean, oh, that's right.
It's like don't waste your time. You don't.
Yeah, it's fine, yeah, but then, it's dependent on how, you get it runs. Yeah. But like I said, it's, case, so. Yeah, I think that's.
Okay.
I think it works. Okay, cool. All right. Can somebody tell me how you do this calculation if you have done it already? And I'm sorry, I did forget to explain what the variables are, but hopefully you all have seen versions of this already in our different data formats, so it's not too confusing what each of these are.
So that's the square root of epsilon.
Yeah.
By the keyword.
Yep, that's right. So that is. And I'm gonna do numpy dot square root just because I sometimes have issues with doing this power function. And oh, sorry. We do need to do numpy dot square root n squared. We get to n. And then this is minus 3/2. Okay. No, I actually quoted on line. Oh, we messed up the spelling for square root. Oh, oops. You already have a value. I will also make sure that. What? Why is it not the phone?
You have to run all.
Oh, that's right. I was like, if I have the problem set the number, I have on something is really wrong.
Never good.
I have a lot of them.
Yeah, I haven't, yeah, that's a good.
Yeah, sorry, I would do the mean of that.
Okay.
Yes. This goes, yeah, you're,
Just say, yeah, which one do you want? Yeah.
Yeah. One.
Hey, I have a quick, wait, so the equation in the slides is epsilon, square root of epsilon multiplied by the points of frequency is the -3/2. But here you're doing the square root of ms cubed and then all of it in parentheses. I guess I'm looking.
yeah, because it's n squared and you want n.
Oh, it's n squared.
Yeah.
Oh, okay, gotcha.
Yeah, so that gives you an estimate of the septum scale of about 0.4 meters. Kind of small. So as you can see already, the fact that the Beofinger is fairly stratified is coming into place. Yeah, so the square root of epsilon times this n squared, because this squared. Oh, that's n squared. That's n squared. Oh, and then power is the minus. Yeah, so then let's run through the library. This is just kind of the standard, values, you know, like, have, noise can be explained, but instead of that, standard. And this is background X-dot value. This is also from the FC, and they tend to have a nice donut cost and out of understand watts per kilogram. So that's kind of what I have set it to. And then there's some additional methods here that I won't go into, but you look at the Mars documentation, you can look through it as well. And this is specifically is for you with like raw data. So this is you have just at the sampling rate of the and temperature and salinity. If you run this method, you'll get better. It identifies the overtones a little bit. Right, so let's run through this. And this lists some different diagnostics on COVID. It's fine. All right, so the first thing that this algorithm does, so this is an example profile. Hopefully everyone can see there's some, this is potential density. There's some unstable density feature that's happening. Fixing depth is actually about 30 meters here, right? So you can kind of see this is happening in the like layer right below the mixed layer, the transition layer. We run here. So this is the algorithm is gone in and found statements. So this is that idea of how far water concepts have to travel to make this a stable density grading. So already so already you can kind of see there's big scale difference here. About 5 meters, these fossils have to travel to get to the most stable density gradient. And if we run through the code, again, like I said, there's multiple ways of thinking about tracking. I just kind of use the standard method here. You can read through that. And yeah, so the algorithm goes and finds a good stratification value. And like I explained, this is just picking the endpoints and what temperature and salinity are. At the endpoints of the overturn and just getting a stratification part. That's what this particular method is using. And you can play around and see how different that looks with different methods. And then the final here, if you a comparison of precipitation calculated from the Thorpe scales compared to precipitation from our measurements. That is several orders of magnitude different. So what could be going wrong here? What to people have ideas for why these might be so different? I'll pull this up a little bit so you can see what these are. And again, there's some black flags, except the algorithm goes. In this case, we just had a pretty good example of the profile, so you can project anything. But it does have some example, some flags, so that's technically, this is giving you dissipation. So it's still making the case that this has gone through the energy cascade and the scales of the so obviously that's yeah, could be that. That is true though, that our ultraviolet scale works. With some effects from starting each one. Any other ideas? So you remember from the slides, what we're measuring, this is just us at the end of this last week, and next week, we'll probably here. And so with this XC measurement it's giving, it's just a point in time, right? It's a particular state at which the overturn was, and it's a particular kind of structure of the overturn, right? It could be kind of in that perfect wave shape. It could be the form where there's multiple visibilities happening, and there's a lot of other gradients and density within this overturn. And so these are actually telling you two very different things. This is an instantaneous measurement, and this is almost an average of what the mixing could happen for the full year. It looks great. You accept that, okay. And I guess we don't have much time to do this, but something we can do is to now look at a bunch of overturning examples. The how these values compare. I think I gave this to you guys as an activity to do, and you are welcome to do it. What I might do is just run my code, and we can kind of see what that looks like, what the data actually looks like. Oh, it's gonna take 5 minutes. Walk through all of this, da da da, la la la. Oh, no. Oh, it's fine. Yeah, so this is, I did a kind of, I just compiled all of the time over the concept period. So this is the top statements. And like I said, this is approximately where everything here is. All the times and the times of India. And if you take the black line, and you see and you can see as you start sort of, this is a like extreme example, but as you start averaging multiple events, start kind of approaching closer to our actual measure of destination. So that's just something like a caveat for this method is just you are kind of thinking of dissipation and some way to hopefully that. But I will leave this as an exercise for you all to do as well. You can play around with it and see you know how many events you need to average over to kind of get a good comparison to dissipation. I just did well, yes. Yeah, so when you're going to a ship with, you know, a CTD sensor, you're probably sampling different points on the overturn spatially. And it's just, you know, over time, you're also sampling as it evolves in time as well. A bit of a you're not getting the full story with the way we sample. So you kind of need to look at it in a sort of average sense. And something Gunnar and Arno and others in the lab are thinking about is how these different methods of getting the patient compare. If you have a stable density profile, very likely it's going to drive mixing. And so they've done some experiments kind of following an overturn on a ship and using FC as well, kind of, and it's not an exact science. It's hard to replicate staying in a stationary place. I'm curious if maybe moorings will be a better way to do it. But it seems like things that people are still trying to understand this. We now have the kind of scale of turbulence measurements to make this kind of impact. And I will leave this as an exercise to the reader, but the last thing that you can do, considering we do have measurements of epsilon as well as the Thorpe scale. You can make a plot that can show comparing orthodox and Thorpe scales. I can pull that up again. Let's see if I can find that. You can do something like this. The data that I have from this with all that I've given you all, you can also do this with our actual measurements, see how these might compare. I will leave that all. And if anyone has questions, the actual, yeah. Because yours would be. Yeah, it's based on, like papers like this that have done these comparisons before and just. Yeah, I'm pretty sure it does, but this is like, this is the same thing with, assuming a constant mixing efficiency. It's like one of those assumptions. You just assume there's a constant value. I mean, if you actually have measurements of mixing, you can test that, but if you don't, there's no, yeah. Yeah. Yeah, that would be my yeah. But I mean, I think I asked Arnold about this because I have not read all the statements about this, but he did say that between 0.8 to 1, somewhere within that, it's kind of between like 0.8 to 1 is typically where your values lie. The alpha values lie. Oh, what is the 0.8 to 1? Yeah, so between 0.8 to 1. Oh, okay, yeah. Oh. Any other questions? Yeah, if you're interested in using this, if your project is interested in using Thorpe scales, feel free to ask me questions. I can also help you get the raw data, find identify smaller return. Definitely can't do with the kind of billing we do with the right now. Yeah. Happy coding. Yeah. So yeah, we'll meet back again in an hour. Have take a break. Oh, actually, sorry, Ellen. 12:40. Like if you wanna, yeah.